What's up guys, it's Simon Fiaz and today's video is on question 2018 equator level chemistry paper 1. Question 1. Complete the figure 1 and it is a Born-Haber cycle. So this one is obviously going to be first ionization energy, of magnesium, second ionization energy for magnesium, and of oxygen. So oxygen stays the exact same. Nothing happens to oxygen because we're not trying to find first ionization energy for oxygen or second ionization energy for oxygen. We're trying to find the first and second. And then here, the atomization energy for oxygen. First electron affinity, for oxygen. Calculate a value for the enthalpy of lattice formation for magnesium oxide. So I know enthalpy of formation for magnesium oxide is minus 602. So what I'll do is I'll do minus 602 equals enthalpy of atomization energy for magnesium 150 plus 150 plus plus one dissociation enthalpy for oxygen, but it's a half of it, a half times by 496, plus first ionization energy for magnesium plus 736, plus second ionization energy for magnesium 1450, plus first electron affinity for oxygen, so minus 142, plus minus 142, and then plus second electron affinity for oxygen, plus 844. And what's the thing I'm trying to find out? Enthalpy of lattice formation is this arrow, so plus this x value. Rearrange it and you should get minus 3888 kilojoules per mole to the power minus 1. Question 2. Calculate partial pressure of each gas in this equilibrium mixture. And I know that's nitrogen and hydrogen mix in a 1 to 3 mole ratio left to reach equilibrium in a flask at a temperature of 550 Kelvin. Equation for the reaction between nitrogen and hydrogen is shown. When equilibrium was reached, the total pressure in the flask was 150 kilopascals and the mole fraction was 0.80. 0.80. Calculate partial pressure. So I know the mole fraction NH3 was 0.80. Nitrogen hydrogen 1 to 3 molar ratio. And I want to find out partial pressure of nitrogen and hydrogen. Now, what I need to memorize firstly, well, you shouldn't memorize this equation, is that the idea that the mole fraction is, the partial pressure is a mole fraction times by total pressure. So what I can do is firstly find out the partial pressure for ammonia. So for NH3, it's just going to be 0.80 times by 150. 120. Now that's for ammonia. So now to find out the remaining Well, I know total pressure is 150 minus 120. I've got 30 kilopascals remaining. And I know nitrogen hydrogen 1 to 3 mole ratio. So all I have to do is I know now that 1/4 is nitrogen and 3/4 is hydrogen. Or I know 1/4 is going to be nitrogen, so 1/4 times by 30, 7.5. And I know the total pressure must add up to 150. So 120 plus 7.5 is 127.5. 150 minus that, 22.5. So slightly tricky question. Give an expression for the equilibrium, because I've never seen this type of question. Obviously I have now, and maybe a bit before when I went through this past paper a while ago, but yeah, it's a bit of a weird question. 2.2, give an expression for equilibrium constant Kp. That's curly brackets, so it's going to be partial pressure of the products NH3 squared divided by the partial pressure of nitrogen times by the partial pressure 3 moles of hydrogen, partial pressure of hydrogen cubed. Perfect. Curly brackets, products over reactants, and remember if you've got a mold you need to include it. Calculate value of equilibrium constant Kp for this reaction and give it C units. So Kp then is just going to be, I'm just going to substitute into there. I'm not going to write it down. Substitute into there. 1.10 times by 10 to the power 3 squared divided by partial pressure of nitrogen 1.20 times by 10 to the power 2 times by 1.50 times by 10 to the power 2, and I've got 3 moles of hydrogen, so that's going to be cubed. I get 2. I guess I'll say 3 times by 10 to the power minus 3. Yeah, there's 2.98, so I said 3.0 times by 10 to the power minus 3. Now the units, well, I know the partial pressure in this case is kilopascals, so it's just going to be kilopascals squared divided by kilopascals times by kilopascals cubed, which is kilopascals to the power 4. That cancels out, I've got 1 over kilopascal squared, that is kilopascals to the power minus 2. And the answer is 3.0 times by 10 to the power minus 3 for Kp. Enthalpy change is minus 92. State the effect, if any, of an increase in temperature and the value of Kp for this reaction. Now I know increase in temperature will affect Kp. So it definitely will affect. But what will happen? Well, the enthalpy change is minus the exothermic. So what's the effect of increased temperature? Well, I know delta H is negative, given just told me that right now. And therefore, if I increase the temperature, it's going to shift to the because the forward reaction is exothermic, therefore if I increase temperature, it's going to shift to the endothermic direction to oppose increased temperature, therefore it's going to shift to the left hand side, so therefore I'm going to get more reactants. So say the effect on the value of Kp, well, it's going to decrease. Reason being, well, this bit you need to be very specific because it's going to be 2 marks. This part, equilibrium shifts to the left hand side, the endothermic direction, to oppose the increase in temperature. Temperature hence decreasing temperature. Question 3, calculate entropy change for this reaction between ammonia and oxygen. So entropy change is entropy of products minus entropy of reactants. So entropy of products, well, I know that I've got 4 NO, so I'm just gonna put in a calculator. It's just gonna be 4 times by 211 plus 6 times by 189. Yeah, you just use the moles times the S value, so it's gonna be 4 times by 211 plus 189 times by 6 minus entropy of reactants 4 times by 193 plus 5 times by 205. But you have to be careful when you just put that in the calculator. You need to actually, like, it will give you a different answer to what you're expecting because the calculator doesn't process it like that. There you go. So you need to add 2 sets of brackets around it, and you should get 181. So 181, it already gives me the units, which is nice, but remember the units is joules K to the power minus 1, multiplied power minus 1. Calculate value for the Gibbs free energy change for the reaction at 600 degrees Celsius. Now delta G is delta H minus T delta S. And I know delta H in the question is minus 905 kilojoules per mole to power minus 1. Minus 905. Minus the temperature, well, I need it in Kelvin, so 600 degrees Celsius is not important to me. The value in Kelvin is, so 600 plus 273, 873 Kelvin, minus 873 times by delta S. But remember, delta S is in kilojoules per mole to power minus 1. I want the final answer in kilojoules. So I need to convert this joules into kilojoules, so it's going to be times by 181 divided by 1000. Put that in the calculator. And I get minus 1063. So a lot of tricks for just 2 marks. A lot of tricks. Then it says the reaction between ammonia and oxygen was carried out at high temperature. Explain how this change affects the value of delta G, Gibbs free energy change for the reaction. Well, the reaction between ammonia and oxygen was carried out at a higher temperature, well, I know the forward reaction is exothermic, so if I increase the temperature, it's going to shift in the backwards direction, aka the endothermic direction, to oppose increasing temperature, hence decreasing the temperature. So I'm going to get more of this. And now entropy changes entropy of products minus entropy of reactants. Now if I've got more reactants and entropy of reactants increases, well, it's going to be like 10 minus example 12, for example, but instead this 12 now becomes 15. What happens, instead of getting minus 2, I get minus 5. So I get a more negative entropy change. So what will happen to Gibbs free energy change? Well, if the entropy change is more negative, it's going to be delta H minus even more negative. So it's basically adding it now because 2 negatives make a positive. So what will happen to delta G? Well, Gibbs free energy change becomes more negative. Sorry, yeah, become more negative, and the entropy change is positive. Well, actually, what I would prefer to say is, I would just say it like that, but I would, entropy change is positive. Or you could say minus T delta S becomes more negative. That's what I like to say. And question 3.4, platinum acts as a heterogeneous catalyst in reaction between ammonia and oxygen. Now, I haven't actually gone through this, but it is part of the question, so I guess I'll just see what the mark scheme says. So, reactants absorbed onto the platinum surface. Reaction on the surface So reactants absorb into platinum surface, reaction on the surface slash bond breaking and then the deabsorption of the product. desorption of the product. So reduce the change of oxidation state when NH2 is oxidized to NO of nitrogen. Well, in this case, nitrogen is going to be -3, and in this case, that's obviously going to be +2. So it's going to go from, well, I'll just say +5. To go from -3 to +2, you just add 5. Or we could say oxidation state changes from -3 to +2. 3.6, when ammonia reacts with oxygen, nitrous oxide can be produced instead of NO. Given the equation for this reaction, classic equation question, 2NH3 plus 2O2 arrow N2O plus 3H2O. 2NH3 plus 2O2 arrow N2O plus 3H2O. Question 4.1, give the full electron configuration of the calcium ion Ca2+. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6. I guess you could say 4s0, but we'll just leave it as that. So the second ionization energy of calcium is lower than the second ionization energy of potassium. Well, in calcium, the outer electron is further away from the nucleus. More shielding in calcium. It's that simple, these kind of questions. They're just looking for extremely, obviously the marks seem extremely specific, but while the second ionization energy is lower, outer electrons further away from the nucleus, more shielding. Obviously I would say Ca in Ca+, but yeah, calcium should be fine. Identify the S block metal that has the highest first ionization energy. It is going to be beryllium. Just look on your periodic table, beryllium, or Be. Give the formula of the hydroxide that is the least soluble in water. It's going to be magnesium hydroxide. It's the least soluble in water. Question 4.5. A student added 6 centimeters cube of barium chloride solution to 8 centimeters cube of sodium sulfate solution. Okay, given ionic equation for the formation of the precipitate. So barium chloride and sodium sulfate. Sodium sulfate Na2SO4. But ionic equation for the formation of the precipitate. So the precipitate, barium chloride and sodium sulfate, is going to be barium sulfate is going to be formed. Alright, so it's just going to be Ba2 plus aqueous. It doesn't really ask us for, it doesn't ask us for state symbols. Ba2 plus SO42 minus form BaSO4. Ba2 plus SO42 minus to form BaSO4. Show by calculation which region is in excess. So first thing I would do is find out the moles of barium chloride. So 6 divided by 1000 times by 0.25. Then find out the moles of sodium sulfate, Na2SO4 equals 8 divided by 1000 by 0.15. And then you can just compare the amount of moles. And you should find out that barium chloride is in excess. It's the bigger number of moles, barium chloride. Then it says total volume of other reagent. Calculate total volume of other reagent which should be used. So the filter contains only one solute. Total volume I want the other reagent is obviously going to be sodium sulfate. So the volume, so the filter contains only one solute. It's going to be 10 centimeters cubed of 0.15 moles deionized cube, because then I'll get the same amount of moles for barium chloride and sodium sulfate. Sodium sulfate. Okay, 4 marks. State whether isotopes have identical chemical properties, calculate percentage abundance of 88 SR isotope in sample, and then it says, okay, so why they have identical chemical properties is because it's got the same electron configuration. Same electronic configuration, or we could say, yeah, same electron configuration. You can't say same number of protons or neutrons. That's a nice part. Then the other part, calculate percentage abundance of 88 SR isotope in the sample. Well, I know relative atomic mass is 87.7, and I know I've got 86 SR to 87 SR is 1 to 1. So it's just going to be 86 times by x, so 86x plus 87x. Now what happens to the 88 SR? Well, now I've got 2x, and 88 SR is just going to be 100. So it's going to be the, obviously, plus your 88, and then it's going to be the 100 total percentage of abundance, total 100 minus your 2x divided by 100. Obviously, you rearrange it and you should get x is equal to 10%. The rearranging part is probably not as complicated, I guess, for most students. It's the construction of this expression. Well, that's 1 to 1, so that's 86x plus 87x. Well, 88, well, 100 is a total, so 100 minus these two x's and times it by 88 divided by 100, and you should get x is 10%. No, sorry, yeah, x is 10%, but it wants a percentage abundance of 88 SR isotope. Ooh, so now what I need to do is 88 bracket 100 minus 2 bracket 10. Almost got it, lost a mark. So 100 minus 20 is obviously going to be 80. So therefore it's going to have a percentage abundance 80%. So that final trick is very tricky. Then this is identify the ion with the longest time of flight. Longest time of flight, so it's going to be the heavy sign. So it's going to be 13A, Ba. Because it's iron, it's going to be positively charged. 3A, Ba plus, which is expected. Then question 4.8. This ion travels through the flight tube with the kinetic energy of that. The ion takes this long to reach the detector. Calculate the length of flight tube in meters, 5 marks. So it only gives me one ion, which is fine. But what I'm going to have to do firstly is I want to find out the length of the flight tube. I can't just work it out immediately. I'm going to have to work out all the steps. I've got the kinetic energy. I've got the time. What else do I need? Well, I need a mass. Do I know the mass of the flight tube? No, I don't. Of the ion? No, I don't. So that's the first thing I would do, is the mass of the 137 Ba plus ion is going to be 137 times by 10 to the power minus 3 divided by 6.022 times by 10 to the power 23. Why else would it give us Avogadro's constant? They want us to use it. Now I've got the mass, I can find out, well, in order to find out the length of the flight tube, velocity is distance over time. Therefore, distance is velocity times by time. So I need to find out the velocity. I've already got the time. I need to find out the velocity. So how do I find the velocity? Well, the velocity is rearrange it. So 2ke divided by square root it. So it's going to be square root of 2ke divided by m. And now substitute values in. I've got the kinetic energy. 3.65 times by 10 to the power minus 16. 2 times by 3.65 times by 10 to the power minus 16 divided by the mass of the ion, which I just worked out. That will give me the velocity. Now let me put that in a calculator first. So square root of 2 to my 3.65 times by 10 to the power minus 16 divided by 137 times by 10 to the power minus 3 divided by Avogadro's constant. Get the velocity. But I want the distance, so the distance is going to be the length of the flight tube. It's going to be the velocity times by the time, which is 2.71 times by 10 to the power minus 5. And I get 1.53, or 54 to 2 decimal places of 3 significant figures. So yeah, find out the mass, rearrange it to find out velocity. Find out velocity, distance to velocity, time by time. That's it. Question 5.1, state the meaning of the term strong acid. Completely dissociates to form H plus ions. Completely dissociates to form H plus ions. In experiment, this much hydrochloric acid adds this much barium chloride solution. Calculate pH that forms at 30 degrees Celsius. So, first thing I would do is (10.35 divided by 1,000 times by 0.10). Now I've got the moles by using moles of concentration at volume. Now I want to work out HCl. So I'm going to use expression HA plus OH minus to form A minus plus H12. I need to times this by 2 because 2 moles of hydroxide ions. So if I do that, 3.75 times by 10 to the power minus 3 times by 2, 7.5 times by 10 to the power minus 3, 7.5 times by 10 to the power minus 3, I'm obviously going to minus that by 1.035 times by 10 to the power minus 3, so I get 6.465 times by 10 to the power minus 3. Let me just double check one thing. Yeah, these are the moles. Yeah. Now see if I minus 1.035 times by 10 to the power minus 3 from here, I get 0. I'm going to find a pH solution that forms at 30 degrees Celsius. Technically, I should add 1.035 times by 10 to the power minus 3. I get 1.035 times by 10 to the power minus 3. Yes, but all I need to do now is Kw is concentration H plus times by concentration OH minus. I know H plus therefore is Kw expression, which is 1.47 times by 10 to the power minus 14. Don't always assume. If it doesn't give you in the question, then you assume it's 1.0 times by 10 to the power minus 14. If it gives you a value, you have to use it. Divided by 6.465. But remember, this is the moles of hydroxide ions. So now I need to find out the concentration of hydroxide ions. And I know moles of concentration of volume. Concentration is the moles divided by the volume. So it's going to be 6.465 times by 10 to the power minus 3 divided by the volume, which is just going to be 10.35 plus 25 plus 10.35, obviously, times by 10 to the power minus 3 divided by 35.35 times by 10 to the power minus 3 power minus 14 divided by 6.465 times by 10 to the power minus 3 divided by 6.465 times by 10 to the power minus 3 divided by 35.35 times by 10 to the power minus 3. Then I substitute pH minus log 10H plus, because remember pH is minus log 10 H plus, and then I substitute that into there, this whole answer, and I get pH as 13.10, and always give pH 2 decimal places. Whew. Very tricky question. Actually, I wouldn't say tricky, it's just a very long, complicated question. But yeah. Question 5.3, give the reason why water is neutral. Concentration H plus equals concentration H minus. Because I've seen trickier questions than this actually, with buffer solutions obviously. Identify the oxide that can react with water to form a solution with pH equals 2. It's going to be sulfur dioxide, SO2, reacts with water to form a solution pH equals 2, sulfur dioxide. Give an expression for the acid association constant Ka for ethanoic acid. So it's just going to be CH3COO minus H plus CH3COOH, and Ka, obviously remember, is square brackets as well. A buffer solution contains this much of sodium ethanoate dissolving this much ethanoic acid. Sample of that is added to buffer solution. Calculate pH of solution formed. Okay, this one's definitely going to be tricky in my opinion. How many questions have I got left? Question 6 I can't do, I haven't gone through that. Question 7, complex aluminium ion. No, I've gone through benzodioxide acid, but I haven't gone through the rest of these, so no. That's question 7. Question 8, yes, I can do that. Easy. Yep. And question 9, I can't do that. And question 10, we'll have a look at it. I think that's the last question. Yeah, that's the last question. So only not that many to go. It's question 6, question 5. So first thing I would do is, I've got moles of sodium ethanoate dissolving this much of moles of ethanoic acid. So I'd work out the moles of ethanoic acid. That is always the first thing I would do. Work out the moles, because they give you marks for that in the exam. And you know, you don't want to just spend so much time looking at the question and not knowing what to do. First, work out the things that you know you're probably going to get some marks on, calculate the moles, and then figure out, okay, so now I need to do this or this or this, for example. So now I've got the moles. Now I'm going to construct the equation, and then I know a sample of this is added later on to the buffer solution. So what I want to do is firstly construct the equation HA plus OH minus to form A minus plus H2O. And H2O, remember, I don't care because that is not in Ka expression. So the moles of HA, in this case, ethanoic acid, 0.035, moles of HCl, 0.01. So I'm going to minus 0.01 minus 0.01 because that's a smaller value. And in this case, I'm going to add 0.01. 0.01, 0, 0.035 minus 0.01, 0.025. And these are obviously going to be the moles, just to clarify. Then I know I did this wrong. I did this wrong. I did this wrong. Because a buffer solution contains this, then we add the HCl. That's what I missed off. Okay, now I've got the actual moles of what I'm supposed to work out. Then I know this much hydrochloric acid is added, so then I'd work out the moles of HCl, which I've already worked out as 0.01. And because it's an acid, H plus A minus, HA, and I know that's 0.01. I know the A minus is 0.025, so I'm going to minus 0.01. That'll give me 0 minus 0.01. That'll give me 0.015, and 0 plus 0.01. That'll give me 0.01. Now I can find out pH. Well, firstly, I need to construct Ka expression. Ka is H plus A minus divided by HA. And I need to work out H plus. So H plus is going to be Ka divided by HA divided by A minus. So now it's just going to be substituting it in. Ka is 1.76 times by 10 to the power minus 5 times by HA, which is I want the concentration, so I need to divide it by the volume. But the thing is, the volumes will cancel out anyway. But in the exam, I would always show that. Yeah. What I would do is divide it by the total volume, which is just 500 plus this 5, so 505 times by 10 to the power minus 3. But in this case, the volumes will cancel out anyway, so it should be fine anyway. And then I've got the H plus, then I know pH is minus log 10 of H plus minus log 10 of my answer, 4.93. No, that's not the right answer, so let's see where I went wrong. Oh yeah, HA is 0.035 originally. I already had that from the part A, from this part. So then I add 0.01, so I get 0.045. That was a mistake I made. And then you substitute the values in, and then you should get 4.28. And let me just double check, that's the only mistake I made. 1.676 times by 10 to the power minus 5 times by HA 0.045 divided by 0.015. That's H plus minus log 10 of my answer. Yeah, 4.28. So yeah, that was a mistake I made. Obviously the volumes will cancel out anyway. Question not 7. Question 8. Using knowledge restriction bonding container of sodium bromide has a high melting point of sodium and a high then of sodium iodide. So stage 1, sodium, Na. Na has metallic bonding. bonding between the positive ions and the delocalized electrons in Na. Na has a giant lattice structure. That should say stage 1. Stage 2, NaBr / NaI, or ionic bonding in NaBr and NaI, sodium iodide. There is bonding between the positive and negative ions in sodium bromide and sodium iodide. NaBr and NaI have a giant lattice structure. And then I'd say stage 3, comparison of bonding. Well, the ionic bonds are stronger than the metallic bonds. Stronger attraction between the positive and negative ions in sodium bromide than in sodium iodide. Why? Because the Br minus ion is smaller than the I minus ion. And that is it for question 8.1. Question 8.2, given equation for reaction occurs when sodium is added to water. Sodium plus H2O will have formed sodium hydroxide plus a half H2. There we go. Given the calculated volume of the gas formed at this much, so I'd use PV equals nRT. I want the volume, so V equals nRT divided by P. And I need to find out the moles of the gas. So I need to find the moles of sodium. No, sorry. I need to work out the moles of hydrogen. The gas formed. That's not a gas. Sodium hydroxide. Actually, maybe that's a solution, isn't it? Yeah, a gas formed is the hydrogen. So moles of sodium is going to be 250 grams divided by 10 to the power minus 3 divided by the mol, 23, 0.0109, and therefore to find out the moles of hydrogen is going to be 0.0109 divided by 2, 5.45 times by 10 to the power minus 3. Times by 8.31 times by the temperature, which needs to be in Kelvin, and I've got the temperature in degrees, so I need to add 273, 298 Kelvin, divided by pressure, obviously in pascals, so 101,000. And then this will give me the volume in meters cubed, 1.33 times by 10 to the power minus 4 meters cubed. Because remember, volume's always measured in meters cubed. Then I want it in centimeters cubed. I've got centimeters cubed dm cubed meters cubed. I want to go from meters cubed to centimeters cubed. I need to divide by 1,000 and then divide by 1,000 again. So I need to divide by a million. Yeah. I need to do 1.3 times 10 to the power minus 4 times by 10 to the power. Actually, no, I got it meters cubed. It's the other way around. Meters cubed, dm cubed, centimeters cubed. So to go from meters cubed to centimeters cubed, I need to times by a million. If I times by a million, then I get, this will go, and then times by 100 again, so I get 133 centimeters cubed. Calculate concentration of sodium ions in a solution produced in reaction question 8.2. Concentration, moles concentration, volume concentration is moles divided by the volume. Moles of sodium ions 0.0109 divided by the volume, and 1 divided by the volume of this total 500 times by 10 to the power minus 3. So it's just testing, will you use the volume of this? No, gas, the volume of the gas formed, which is hydrogen. Then you get that, and you should get 0.022 moles per minus cube. 8.4, draw the shape of NH2 minus sign. This is iron. I'm going to use square brackets, should be square brackets. Got minus here, NH2, so I've got my nitrogen, hydrogen, hydrogen, and it's going to have no pair of electrons. Including, yeah, predict the bond angle, 104.5 degrees, reason being, four electron pairs repelled to be as far apart possible. Lone pair repulsion greater than lone pair bonding repulsion. And then you can also say which is greater than bonding, but then bonding pair repulsion. Question 9 can't do. Question 10. Student added this much hydrated sodium carbonate. This much hydrochloric acid. After reaction is complete, the resultant solution was transferred to a volumetric flask made of 250 centimeters cubed with deionized water and dark. Several of this titrated with this much sodium hydroxide. Mean title is this much of sodium hydroxide. Calculate value of X. So, in order to calculate the value of X, I need to find out the moles of this, because I've got the mass. Moles is mass over MR. Once I've got the moles, then I can find out the MR, mass divided by moles. And then once I find the MR, I can work out total MR. I can work out X. So, first thing I do is find out the moles of HCl. 0.250 times by 200 divided by 1000. After reaction is complete, the resultant solution transferred to a volumetric flask made of 250 centimeters cubed mixed thoroughly. Several of this is titrated with this. Then work out the moles of sodium hydroxide, which is going to be 1000 times by 0.150. Because several of this target with this, the mean type was this of sodium hydroxide, so it's going to be that times by 0.150, which will give me 3.99 times by 10 to the power minus 3. And this is with 25 centimeters cubed. And I want to make up to 250 centimeters cubed, so now I need to times that by 10, which give me 3.99 times by 10 to the power minus 2 moles. Then I want to work out the moles of HCl reacting with that. And how do I do that? Well, I can work out do 0.050 minus 3.99 times by 10 to the power minus 2, which is 0.0101 moles. If the moles of this divided to that is 2 to 1 mole ratio, I need to divide by 2, which is 505 times by 10 to the power minus 3 moles. And then I can work out, now I need to convert this milligrams to grams by dividing by 1000, so it's going to be 0.627 grams. And then all I do, moles of mass of MR and moles of mass. Moles of mass of MR and moles mass divided by moles, so it's going to be divided by that. And that will give me the MR, and then minus the MR, this total thing, so minus 106.18. So this has to be MR of 18. H2O is already 18, so therefore X is equal to 1. And that is the end of this paper.